Okay, so we're going to do river crossings now. If you can see that, girls, can you? River crossings. So let's supposing in river crossings what we use is vectors, which we know all about now, how to use vectors, and trigonometry. So triangles, a lot of relative velocity is to do with, of course, triangles. Now then, let's take a river. The river is d meters wide. And you're on the south bank and you want to head across to the north bank. So you head across a river. So there's your heading vector. A couple of things to take into consideration. You head across the river and you head across the river at an angle theta to the bank. So this is a velocity vector. Another thing that's there is the river velocity. So the river normally has a current flowing. So this is the direction of the current is flowing downstream. And your heading vector is the relative velocity vector. So that blue line here is the VBR, the relative velocity vector. So the way you head, the VBR, your heading vector is always going to be the relative velocity one. Now when you do that, if you start here and you head across the river's pushing you downstream, what actually happens is you end up over here somewhere. So that's your actual velocity. So I'll call that the VB. That's the actual velocity. Okay, so three things to consider there. Your heading velocity vector, the blue line, the actual velocity, the red line, and the green vector, that's the river current. Right, now let's consider a couple of situations. So first of all, let's supposing you have a river and you are here. You wish to cross that river in the shortest possible time. You don't care where you end up. So you head across the river. You head straight across because what you've got to do is cross in the shortest possible time. The river current is going to push you downstream. So this is my heading vector, VBR. Green line is the river. What happens? I end up down here. So that's my VB. Sorry, my VB. Now, important thing to consider. This is my relative velocity. Remember, the relative velocity is the heading vector and it makes an angle with the river. So this is my angle here, theta. And of course you can see here, if it's the shortest possible time, then theta is going to be 90 degrees. So this crossing vector is only made up of one component, and that's the j component. There's no I component. Okay, so two things that we can work out using this kind of idea. So we can find out how long it takes to cross the river. If I said that river was d meters wide, how long does it take to cross the river? So that's going to be distance over speed. So d over, the speed is the vector that takes you across the river. Now the vector that takes you across the river is VBR. So that would be d over VBR is the time to cross the river. And if I said VBR by the angle here that takes me across, that's a sine of 90. And of course, VBR by the sine of 90 is just going to be VBR. Okay, what's the distance downstream? That's the other thing I often have to consider. So if I cross, how far downstream do I go? So I started here, but I've ended up down there. So what's the distance downstream? Remember, the distance downstream is time multiplied by the speed that takes you downstream. So what speed actually takes you downstream? In this particular case, it's only the VR. That's the only one. So this is going to be crossing time, which is t, which is this, d over VBR, multiplied by the speed that took you downstream, multiplied by TR. Okay, So that's the shortest time condition. Now the second condition is with the same river, d meters wide. This time we want to cross by the shortest route. The shortest route. The shortest route means if I'm here, I want to go straight across. I just want to cross that river. I want to get there. I don't want to head upstream or downstream. I have to collect someone on that side, so that's where I've got to be. The river current, of course, is pushing downstream. So if I want to cross and get straight across, I've got to head up this direction. So of course this is my VBR, my relative velocity. This is the angle I make to the bank, that's theta. Now this time you can see that my VBR, it's not quite as straightforward as this one. This in the first one, the VBR just had a J component. Now I'm going to have to find the two components, the I and the J component for the VBR. So I'm going to draw a right angle triangle around this, and I'm going to identify these two lines. I'm going to move this one over here just to make it more obvious. Okay. This, of course, is now I'm crossing by the shortest route, so this is where I want to end up. So this is my VB here. That's going to be my VB. Okay, so that's my VB. Now when I break this blue line into its two components, this one is adjacent to the angle. The VBR is the hypotenuse. So this one will be VBR cos theta, and this one will be VBR sine theta. And you can see now, in this particular case, the VBR sine theta and the VB are the same. They're the same, they will have the same value because I'm crossing by the shortest route. Okay, so let's see, what can I find here? I could find the crossing time. The crossing time is the distance divided by the velocity or the vector that takes me across the river. Now, the one that takes me across the river is VBR sine theta, which happens to be the same as saying d over VB in this case, because they are the same. They're both the same. They're going in the same direction. Okay, and because we're making that same triangle, they're going to be the same. But just remember this one, girls. This is the one. This is the one we'll remember. Okay, and what happens here is that, of course, there isn't a distance downstream because I'm going straight across here. So I'm ending up straight across there. So there isn't, I'm not going X meters upstream or downstream. Now, the third situation, we'll just call this a general crossing. So this is any crossing. The first two are special conditions. First one is the shortest time, second one shortest route. This one, let's take this as a general crossing. We're crossing a river, d meters wide. Let's say that we head upstream. The river is pushing us downstream. So what will happen is we'll end up down there. So that will be our actual velocity. This is the velocity of the river, and this is my relative velocity, VBR. The relative velocity will make an angle with the bank. I'll call that theta. Okay, I'm going to look at the relative velocity's components. Draw a right angle triangle around it again. This will be VBR cos theta. This one will be VBR sine theta. Ignore that VB now, we're not interested in it. Okay, what's the crossing time? The time to cross that river will be the distance divided by the velocity that takes you across the river. There's only one velocity taking you across the river, and that's the VBR sine theta. The other thing I might want to find out is the distance downstream I end up. So the distance downstream this time, so this is where I started and this is where I'm ending up. So that's going to be my distance downstream. From there to there, I'll call that x. So let's find that distance x. Distance, remember, is time multiplied by speed. time to cross the river will be the crossing time t, multiplied by the speed that took me down the river. Okay, so which vector took me down the river? I have this one here, VR. However, this VBR cos theta is going in the opposite direction. So it's pushing you upstream and this is pushing you downstream. So you're going to have to take that into consideration and subtract it from the VR. So that's going to be VBR minus VBR cos theta. Okay, so when we're looking at crossing rivers, we're going to look at one of those three. This one, that last one, number 3, we could also apply it to going downstream. Same idea, same kind of situation. Okay, we'll come across that later on. Okay.